In this video, we are going to answer the question, how do I extract sensitivities from the OP2 file? Now, sometimes you want to do this when you want to move Nastran's gradients to a separate optimizer or to a separate machine learning process. Now, in this list from 1 through 4 are the different ways to get the gradients. Number one, you can put the gradients in the H5 file. You can put the gradients in a text file like CSV. You can output the gradients to the F06 file, or you can output the gradients to the OP2 file. Now, on my side, I recommend using method number 1. It's going to be the most transparent and the most flexible method to move your gradients around in Python. The other approaches are very difficult. These are so-called legacy approaches. They're very outdated in my opinion. They're very not transparent. They're very difficult to work with. So I do not recommend using 2, 3, or 4. So in this video, I'm going to focus mostly on number 1. Now with number 1, this is how you're going to do it. And before I go ahead and talk about number 1, I need to talk about one very important thing. Now, I am assuming you already know how to configure a sensitivity analysis with Nastran. If you're new to how to do that, look on the website for a sensitivity analysis tutorial that will walk you through the process of configuring SOL 200 for sensitivity analysis. Now, if we look at this example, the bulk data file, it's already configured for SOL 200. I already have the objective and the constraint. If I look at my other bulk data file, I already have the design variables, the objective, and the constraints. So I'm assuming you're already here. If you want to perform a gradient analysis, one of the ways to do it is with this command, the dsaprt command. Make sure that end equals sense. This is going to tell Nastran, hey, perform a gradient calculation, but terminate there. Do not continue with the optimization. So here we have end equals sense. And the other thing you want to do, by default, you're only going to get gradients for a few responses. So for example, say you have response R1, this is a stress, and suppose you have maybe 1 million elements. When you perform your gradient calculation, you get gradients for maybe for 3 elements. But you might want gradients for more elements or more responses. The way you do that is with the dscreen command. So let's go ahead and dig it up real quick. Let me dig up this example. And let's call this stress. So this is how you use the dscreen command. If you want more gradients, you lower this first value here. So right now it's set to 10,000, say 50,000. And you would increase this number too. So here it's currently configured to output responses for at most 10 elements. Here you can increase the number to maybe 10,000. So you would get gradients for at most 10,000 elements. And you would do this again with the displacement response and for any other response that you want. So if we look here at this example, we've done this for every response type. Here, let me increase the second number here. Say we want responses for at most 100 responses. We want gradients for at most 100 responses. We want stress gradients for at most 100 elements. We want displacement gradients for at most 100 nodes. That's how you use that entry. So we've gone over dsaprt, dscreen. Let's go ahead and talk about how to output the gradients to the HDF5 file. So all you need to do is add this bulk data entry, HDF5 out. Now, sometimes you'll find additional data on that entry. That's perfectly fine. As long as it has this entry once, you should be able to output the sensitivities. So let's go ahead and run Nastran real quick. So let's go ahead and run Nastran from the command line. Now here we get an H5 file. As always, always look inside your F06 file for any user fatal messages. And here I spelled it incorrectly. User fatal message. Okay, it doesn't look like it's in the file. Okay, good. Now, you might be asking, okay, how do I look inside the H5 file? You can download a tool that's called the HDF Viewer. This tool is available for free at the HDF website. So let's go ahead and find how to download that. So Google HDF view, you get taken to the HDF group website. This is where you would make an account and you would be able to download this program for free. Now, what you do with the H5 file is as follows. Take the H5 file and simply drag and drop it here. Your sensitivity coefficients are going to be in 3 separate data sets. Here I'm navigating to the Nastran result optimization branch. In the sensitivity branch, you'll find your sensitivity coefficients, but they're in 3 separate places. Here, let's look at part of the data here in this table. So this is part of the sensitivity coefficients. So what you would need to do is the following. So here, let's go ahead and open the domains data set. If you look here in this far right column, this is a domain ID column. This is pointing to ID 3, so we'll open the domains column or table, or data set rather. If we look at this row, ID equals 3, we get this entire row. This is telling you the source of this data. If you have 100 subcases, you want to know what subcase this data came from. If you did a transient analysis from 0 to 1,000 seconds, you want to know what second that data came from. This domain ID column is telling you where to look for that subcase data or that time step data. Here, this next set of rows has domain ID 4. So if you look in the domains data set and you find this row where ID equals 4, this gives you this other row. If you look at the subcase column for ID equals 3 and ID equals 4, some of the data is coming from subcase 1, and the next set of data is coming from subcase 2. So what you would need to do is the following. If you were doing this manually, you would need to go into Excel, and bear with me for a moment because there's a faster way to do this. So here would be your stress data set. And then here on this other table would be your domains. So we know this is the domain ID, this is the subcase number. So you would need to manually associate the rows together. There's a faster way to do this, which I'll get to in a moment. Now, where are the sensitivity coefficients? If you look back at this data set, you get 2 columns, position and length, LEN. Position is an index number. Index numbers are going to start with 0, 1, 2, and so on. Here it's pointing to index 6. So if we go and open this other data set called coefficients, it would help if I move this side by side. And here, let me remember. Right. So this is going to be pointing to index 6 in the sensitivity coefficient data set here on the right. So if we go to index 6, which would be this row, this is the start of the sensitivity coefficients for that first response. This first row here on the left, this is the stress response for element 1. This example happens to have 2 design variables. So if we look here, we have here, because of the D-link, we effectively have 1 dependent variable and 2 independent variables. So in the H5 file, we're only going to get sensitivities for the independent variables. So here, even though we have 3 design variables, we only get coefficients for the 2 independent variables. And again, we have 1 dependent variable because we're using a D-link. So if we look here, we get told that the sensitivity coefficients for that element start at position 6 and go on for 2 rows. So if we look here on the right, this is index 6, and here in these 2 rows are the sensitivity coefficient for that stress response for variable x1 and variable x2. Now what you need to do, you need to manually combine all these data sets together to get your sensitivity coefficients. Now, you could do this with Excel manually, or you can do this with Python. Now, I'm going to provide a copy of this Python script that already does that for you. Now, I'm going to show you how to modify this Python file real quick. So in this first argument, you're going to specify the path to the H5 file. In the second path or argument, you're going to specify the location of the data set. So here we see that we went down the Nastran branch, then result, then optimization, then sensitivity, then R-type 1, and then stress. If you look at the HDFI program, this is basically going down the branch here on the left. So suppose I want to get the sensitivity coefficients for displacement. Here I would modify the second argument so it ends with disp or displacement. Disp is the same name of the data set here on the bottom left. And now the last argument would be the location, the name of the text file where you want to output the sensitivity coefficient. So here we'll say disp.csv and we'll run this. So now if we look at our desktop, we see a new CSV file. Now you can go ahead and open this in Excel, and I think I'll do that right now. Now you can see that this has all three data sets. The first few rows would be the displacement data set. So let me close some of these data sets for a quick moment. So let's go ahead and open the displacement data set. So that would be here. So let me color them just so you see. So here are the displacement data sets. These next few rows here are going to be the domains data sets. So let's go ahead and find that data set. So that'd be this data set. And then the last two rows or columns would be the sensitivity coefficients for variables x1 and x2. So that would be here, the displacement, or sorry, the coefficient data set. So that would be here on the right. So if we open all of these up at the same time, I think that gives you a better idea of how this is all organized. So again, you would have to either do this manually, say with Excel or Python, or you can use the Python script that I'm providing today to automatically combine all of this data together. So let's look at one of these sensitivity coefficients. Let's say this one as an example. So it would be this row. Let me go ahead and highlight this maybe with red. Here on the right, or first on the left, we know this is a displacement. If we look at the grid column, this is the displacement or the gradient for displacement at node 4. And here at the subcase column, it's telling it's for subcase 2. Here in the VID column, it's telling us this is for variable 100,001. So that would be variable x1. And then the sensitivity coefficient is 0.02262. So if you want to give us a label, let's go ahead and give it a label of dr1 divided by dx1. And then if we go to the next row, that would be dr1 dx2. And then here we'll say, I'll just annotate this subcase 2, subcase 2. And then you can add more annotations if you want. Now, the great thing about having a CSV file is that this file, you can easily open this file and look what's inside of this. Now, what you can do, you can hand this file off to an optimizer or a machine learning process. You could have a separate script, a Python script that opens the CSV file, reads in the gradients, and you can carry on. Now, let's do this for stress. Here we'll go ahead and modify the second argument, stress. And here we'll rename the third argument. We'll say output this to the stress CSV file. So we'll go and run the script. And now we have this other CSV file. So let's go ahead and open it here in Excel actually and see what's going on. So here you can see that now we're dealing with element IDs. So these are the gradients for stress responses for each element. Here we see we have gradients for element 1, 2, and 3. Here on the right we have our gradients. In the subcase column we're told where the gradients are coming from, subcase 1 or 2. Now a few comments about the Python script. You want to have these imports. You want to import H5PY and HDFI plugin. This is going to help you be compatible with MSC Nastran, what is it, maybe 2021 and newer. If you try and read the H5 file without this import, you're going to get a failure trying to read the H5 file. Now, this script, I quickly updated an older script that I had. So I added a few rows that automatically combines the sensitivity coefficient dataset with every other dataset. So please double check this. I didn't have time to test this for a few weeks. I only did this in maybe 10 minutes. So please test it. Please make sure that everything's being associated together. Now, that's the easiest way. That's the most transparent way. This is the method I rely on 100% of the time. If I am using a separate optimizer, if I'm doing machine learning, I'm using method number 1. Now, there are other methods. At this point, I'll talk about them. I'm not a big fan of these other methods, but just in case you have to, and just in case you're required to use these other methods, just in case you cannot convince your superior to let you use an easier method and you're stuck using this more difficult method, I'll go into each of these methods one by one. The next method is by using a text file, a CSV, and this is how you would go about that. Now here in this other bulk data file, you would turn on this parameter called xyunit52. This is going to let Nastran output the gradients to a text file. So if we rerun this Nastran run, we get a new file called the .52 file. This is going to contain the same gradients. So here, what's going on here, the rows are being cut into multiple rows. So these two lines are actually combined together like this. So these would be the gradients for this response. These would be the gradients. These would be the gradients for this response. So if you look through this, these would be the, I think it might actually help if we output this maybe to a CSV file. So let me see. Right, okay, let's go ahead and replace all the spaces. And let's go ahead and save this as maybe test.csv, just so you get an idea of how to read that file. So let's go ahead and open this. Okay, so you see we have various columns. Let's go ahead and fit that. So this is these two values are the gradients for an element stress. Here you get told what the element ID is. Here you get told what the subcase ID, and you get some other information. Now, when I was starting out with Nastran, what I would do, I would read the text file here. This is very difficult. This is very problematic when you're dealing with more complex optimizations, when you're trying to read gradients for so many responses. This is one of the harder methods. You might be tempted to use this method. I discourage the use of reading this text file. I recommend outputting one of the CSV files like this. This is more flexible to work with when you want to steer the gradients to an optimizer or a machine learning process. Okay, so there is one other thing you can do. I don't know if it's worth mentioning, but I'll just mention it because you might see this in the wild sometimes. You can steer that data to a specific file. You'll notice right now it's being spit into the .52 file. In the first two rows, I have this statement, assign user file. Here I'm saying, hey, anything that was going to that old file 52, you know what? Steer it to the specific file called optimization results. Here, if you want, you can give us a different name, gradients.py. f06.csv. Let's go ahead and save this and rerun this. And if you look here, we'll get a new CSV file, gradients. Now, this is the same text as before, but guess what? You have to go and have a hard time trying to read all this data. So that would be the second approach. Now, the third approach is as follows. The gradients are also written to the F06 file. So if you look here, we get this set of data here: design sensitivity matrix, output responses, sensitivity coefficients. I discourage the use of the F06 file when you want to read data. I've seen, or I'll give you my personal experience. When I first started using Nastran, I would try really hard to read data from the F06 file. It's possible, but you'll be there weeks trying to get that to work. I discourage the use of the F06 file whenever you have to extract data. Instead, use the H5 file to extract data. It's better formatted, it's more flexible, and it's easier to use with Python. So don't use the F06 file. And then the fourth method, OP2. Now, personally, I've never used the OP2 file to manually extract data. I've never used Python or Fortran or C++ to extract data from the OP2, and I'm kind of glad I never did. It seems more involved. It's not transparent. Here, from what I've shown you today, hopefully you're convinced that reading sensitivity coefficients from the H5 file would be the most flexible way, and that's what I'm recommending. So to answer the first question we had at the beginning of the video, how do I extract sensitivities from the OP2? My answer is this: before you read data from the OP2, first try the H5 file. I'll provide the Python file or Python script. Use it, test it out, see how well it works. If it's enough, perfect. You can carry on to do your optimization or machine learning. But if you're required to use one of these other methods, hopefully the other information I had in the video is useful to you. So that's the end of the video, and thank you.